Okay, so now let's get started. So if we look at these equations, um, it doesn't seem like there's any thing immediately that we can use to solve them, right? Because the the second equation has both quadratic and linear terms, so it doesn't really look like there's nothing like obvious we can do here. But for the first equation, we can use this identity. So to relate the terms in the first equation, we have this factorization here that x squared plus y squared plus c squared minus xy minus xz minus yz equals 1/2 times x minus y squared plus y minus c squared plus c minus x squared. So then if we just use this, that means that the sum of those three squares is 2000/9, right? So we just plug that into the equation. And so now there's not much more we can do with this equation, so let's go to the second equation. Um, does anyone have any ideas for what to do for the second equation? Just if you have an idea, type it in the chat. Okay, so nobody said anything, but let's just start simple and set two of those expressions equal to each other, like x squared plus y equals y squared plus c, right? And then we can try rearranging that to get like a difference of squares. And then so then we get x minus y times x plus y equals negative times y minus c. And yeah, so Kevin, so yeah, that's the substitution we're going to be using. And so the reason we're using this is because we see these x minus y and like y minus c, we see those terms again. So it seems pretty useful to set that substitution. So we're going to let a equals x minus c, b equal y minus c, and c equals z minus x. Oh, it got slightly cut off, but yeah. So the first thing we notice about the substitution is that if we add a, b, and c, we get 0. So a plus b plus c is 0. And so if you go to the next slide, I think, you might have to recompile. So a plus b plus c is 0. And from what we had above, x minus y squared plus y minus z squared plus z minus x squared, that means that a squared plus b squared plus c squared is 2000/9. And from here, we can square a plus b plus c and subtract a squared plus b squared plus c squared. And so that gives ab plus bc plus ac is negative 1000/9. So so now it seems natural to go back to the second equation we had with x minus y times x plus y equals negative of y minus c. And we can try using our substitution there. So if we do that, then we can isolate x plus y. And so x plus y equals negative b over a. So does anyone have any ideas for what to do from here? Because we have x plus y, but it's not like we can't immediately write it in terms of a, b, and c right now. Just if you have an idea, put it in the chat. Yeah, so we could so so Kevin said to try substituting C for negative A minus B, and like we could try that, but like our immediate concern is trying to get rid of x plus y and write that in terms of um, A, B, and C. So what we did not use yet is actually, we didn't use this, the other equations, right? Because the second set of equations had multiple pairs. So if we take this pair, like y squared plus z equals z squared plus x, then we obtain y plus c equals negative c over b. So that's what someone said in the chat. And right, so if we subtract x plus y, if we subtract like y plus z from x plus y, then we actually just get x minus z. So we're gonna try that. So if we do that, then we get, oh, that should say negative c. Okay, so now we have, another equation with a, b, and c. So if we multiply this equation by a, b to clear the denominators, then we get that AC minus b squared equals negative ABC, right? So then, so if we did this with the other pairs of equations, like we subtracted, say, if we subtracted x plus z from y plus z or something like that, then we can get like two other similar equations, like AB minus C squared equals negative ABC, and BC minus A squared equals negative ABC. So, another way we can argue this is just by symmetry. But so yeah, now once we have this, this is pretty good because if we add all of the equations, then we get back to a pretty symmetrical form, right? So if we add the three equations, then we get that negative 3 ABC, let's just say negative. So then, so negative 3 ABC equals AB plus BC plus AC minus A squared minus B squared minus C squared. And then we can just use what we had before. And so then we get that this is equal to negative 3,000 over 9. And so ABC is 1,000 over 9. So now we have A plus B plus C, AB plus BC plus AC, and ABC. So then we can just we can write a cubic equation for the roots, that a cubic equation that has the roots A, B, and C. And this is because of Vieta's formula. So we have that the equation t cubed minus 1,000 over 9 t plus, no, minus 1,000 over 9 equals 0 has the roots a, b, and c. So if we, so I'm going to skip the solving of this cubic, but actually we can just factor it. And it turns out that negative 10 is a root of this equation. And so once we use that, then we get that a, b, and c are negative 10 and 5 plus or minus 5 root 13 over 3. in some order. Um, so now we can remember that x plus y equals negative b over a, which is what we had before. And also remember the question asked us to find the maximum value of x plus y. So does anyone want to say in the chat which values of b and a are going to give the maximum value of x plus y? So we're just using those roots in some order. Yeah, so if we plug in negative 10 and 5, negative 5, no, 5 minus 5 root 13 over 3, then we get x plus y is 11 plus root 17 over 2. And so our answer is 11 plus 117 plus 2, which is 130. So does anyone have any questions for this? Okay, I guess not. And so we'll be moving on, and I guess you'll expect an actual problem of the week soon.
Okay, so now that we're done with the sample problem of the week, we're going to go into today's topic of sums. So first, we're going to review some basic properties of sums. So first of all, I'm sure you all are familiar with the notation, but the first bullet point explains it for you in case you forgot. And then there's some basic formulas you should know for sums. So the sum of the first n terms of an arithmetic sequence of the form a plus d, a plus 2d, dot, 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 is going to be n times 2a plus n minus 1d all over 2. The sum of the first n terms of a geometric sequence of the form ar squared, dot, 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 is going to be a times r to the n minus 1 over r minus 1. And finally, the sum of an infinite geometric sequence of the form ar squared, dot, 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 with the magnitude of r less than 1 is going to be a over 1 minus r. So I'm sure you guys have all seen these formulas before, so we're not going to go over the proof. And before we get into anything too complicated, we're just going to do a review question using only basic sum concepts. So if you scroll down, yeah, so this is from 2010 Math Prize for Girls, and I'll give you a few moments to read it. And feel free to type any ideas in the chat. Yep, so it looks like people are saying bash, so bash is what we're gonna do. So first of all, note that we probably have to find p of x. So take a moment, can anybody tell me what p of x is? So note that p is uniquely determined because we have 3 values and it's quadratic. Yeah, so Yash says it's 6x squared minus 3x plus 7. And so that's correct. We have p of x is 6x squared minus 3x plus 7. And now we're just going to plug it into our sum. So when we do that, we're going to be able to split it into 3 different sums based on the power of n. So Kevin is suggesting an easier method, and we're gonna stick with the routine method for now, and we might discuss the easier method later. So going back to what we're doing now, we have our sum split into 3 sums. Which one is the easiest to evaluate? Yeah, so the last sum is very easy to evaluate just because it's a standard infinite geometric sequence. So on the next slide, we see that it's just going to be 1 over 1 minus x. I'm excluding the coefficient for now. So now what's more interesting, I guess, is the second sum. So how are we going to approach the second sum, for example? Oh, yeah, I meant last, not first. Okay, so that's right. We're going to multiply by the common ratio. So if we let s be equal to the second sum of n equals 0 to infinity of n x to the n, we are going to calculate xs. Scroll down. Yeah, so we want xs, and then as many people are saying in the chat, once we compute xs, we're gonna get it to be the sum from n equals 1 to infinity of n minus 1 times x to the n. So we can subtract the xs from s to get a standard infinite geometric sequence. Somebody is asking to scroll up, so could we scroll up quickly? So yeah, feel free to, I guess, copy down the 3 sums. Okay, and let's continue. So now that we multiplied by x and subtracted, we have a linear equation to solve for s. So we divide both sides by 1 minus x, and what we're gonna get is s is equal to x over the quantity 1 minus x squared. So now we have a value for s. So now all that's left to do is compute the first expression. So we're going to try to do exactly the same thing we were just doing. So if we let t be equal to the first sum, or sum from n equals 0 to infinity of n squared times x to the n, let's do the exact same thing by computing x times t. So if we do that, similar to before, we're going to get x times t is equal to the sum from n equals 1 to infinity of n minus 1 squared times x to the n. So this time when we subtract, we're going to get 1 minus x times t is going to be the sum from n equals 1 to infinity of 2n minus 1 times x to the n. 2n minus 1 just comes from n squared minus n minus 1 squared. So after we have this expression, how can we solve for t? Because we can't directly solve right now since we still have a sum. Yeah, so we see that we can actually separate this sum. So if we break it up into the sum from n equals 1 to infinity of 2n x to the n, and the sum from n equals 1 to infinity of x to the n, the first term is actually just 2 times s. And the second term is just a standard infinite geometric sequence, x over 1 minus x. So we're going to plug in our value for s, and we're going to get that t is going to be equal to the quantity x squared plus x over 1 minus x all cubed. Yeah, sorry, I missed an n on the second summation. So now that we have all three terms, we're just gonna put it all together. And I'll spare you the computation. When we solve it, we're just gonna get 16x squared minus 11x plus 7 all over 1 minus x cubed. So the answer is 16 comma negative 11 comma 7. So that's it for our sum review. Are there any questions? Can we go back to the problem? Are you good? Okay, I guess we're moving on to telescoping. So this is our first main method for solving sums. So oftentimes we're not going to get something nice like a geometric sequence or an arithmetic sequence. So when we have something ugly, oftentimes we can write the summed f of I as a difference, like g of I plus 1 minus g of I for some function g. So this isn't always going to work, but when it does, it's really nice because if we try plugging in this expression for f, we're going to get like g of 2 minus g of 1 plus g of 3 minus g of 2 all the way to g of n plus 1 minus g of n. So basically every single term is going to cancel because we have a g of I and negative g of I for all I between 2 and n. So this means that when we try evaluating the sum, only the first term and the last term are going to remain. So this sum just turns into the difference of two terms, g of I plus 1, g of n plus 1 minus g of 1. So there's, since this method sort of telescopes, sort of collapses the sum in on itself, it's called telescoping. So there's some good methods to find telescopic series. In general, you want to find a way to write it as g of I plus 1 minus g of I. So that means trying to find a way to make it a difference. So some common ways to do this is through partial fractions, which or trying to relate consecutive terms. And for trigonometric sums, which we're not going to do today, we can often also use sum to product in order to write a product as a difference. So let's quickly go over an easy example of telescoping. So I'll give you a moment to read the problem, type any ideas. This type of question should be familiar to a lot of you. Okay, so we have 1 over k squared plus k, and a lot of people are noticing that this is just standard partial fractions. So if we can split ak up as 1 over k minus 1 over k plus 1. And in case you've never seen this before, one easy way to notice it is just that k squared plus k is factorable. So you always want to try factoring and then splitting the fraction up. So now that we have this, what does the sum in question telescope to? So we're just going to do standard telescoping, and it's going to be 1 over m 1 over n minus 1 over n. It looks like I reversed the two numbers. It should be 1 over m minus 1 over n. So now that we have this, we can just plug it back into 1 over m minus 1 over n is equal to 1 over 29 and clear the denominators. And yeah, a lot of people are already ahead of me. So once you get this expression, we can factor it using Simon's favorite factoring trick. So what that's going to give is going to be 29 minus m times 29 plus n is equal to 841. So does anybody have a pair which works? Yeah, so m is going to be equal to 28 and n is going to be equal to 812. That's the 1 times 841. And that means our answer is 840. So this is a very routine example of telescoping. The trick of splitting up a fraction as 1 over k minus 1 over k plus 1 appears very often on competitions. So now let's look at a less obvious application of telescoping. So I'll give you a moment to read the question and post any ideas. So some people are suggesting to write the first couple of terms. And this is a good idea to try engineer inducting for a lot of questions. But actually for this question, you're probably going to need a lot of terms in order to notice anything. So the point is, like, we probably just want to find a way to telescope it normally. So if we look back at our strategies, one of the things we can try is to relate consecutive terms. So let's try to relate consecutive terms of this sum. So the point is that when we have factorials, factorials are actually very easy to write recursively. So if we try connecting the only the factorial part of consecutive terms, let's try finding a relationship between k factorial over 2k plus 1 factorial and k plus 1 factorial over 2k plus 3 factorial. So feel free to type in the chat like any relationship between these two expressions. So taking the difference is a good idea, but yeah, as Brian said, we're just going to find the ratio between these two. So factorials, as I said, are really good for finding recursive relationships. So if we just divide them, we can get that k factorial over 2k plus 1 factorial is going to be equal to 4k plus 6 times k plus 1 factorial over 2k plus 3 factorial. And this is really easy to manually check. So now that we have this, we want to somehow put it back into the original equation. So as you can see, 4k plus 6 is actually very close to 4k plus 1. So this may hint that we're on the right track. So anybody have any ideas to plug this expression back into the initial equation? So I guess one thing you can notice is that we want to inject what we have right now back into our sum end. So one way we can artificially do this is just add k factorial over 2k plus 1 factorial and then subtract it. So we note that the sum end is going to be 4k plus 2 times k factorial over 2k plus 1 factorial minus k factorial over 2k plus 1 factorial. And then now that we have this, we can plug in what we just got into the second term to get 4k plus 2 times k factorial over 2k plus 1 factorial minus 4k plus 6 times k plus 1 factorial over 2k plus 3 factorial. So does anybody notice anything nice about this form? Yep, that's right. This actually telescopes. So one way you can see this is that if you plug in k plus 1 for k into the first equation, we're going to just get into the first expression, we're just going to get the second expression. So now that we have this telescope, we're just going to solve it normally. So just as a general rule of thumb, telescope questions, once you find a telescopic relationship, are pretty much a one-line solve. So once we have what we have now, we can just write as f of 0 minus f of n plus 1. And some simplification gives 2 minus the quantity k factorial over 2k plus 1 factorial. So some people are asking for motivation. So this question is a bit hard to do if you don't realize initially that it's telescopic. But so as stated before, a general idea for finding telescopes is to try relating consecutive terms indirectly. So we discard the 4k plus 1 because we need to make a difference eventually. And we include the k factorial over 2k plus 1 factorial because it's really easy to relate this function, consecutive values of this function, as seen like they have an easy ratio to deal with. So are there any other questions? Okay, I guess not. So we are going to move to double sums.
So with double sums, sometimes for a problem, we have to compute a sum whose individual terms are themselves sums. So an example of this would be the following double. So we have an elementary double sum here, where the quantity inside of the first sum is a second sum. So how would we evaluate this expression? So with double sums, what this tells us to do is to first evaluate the inside sum, and then sum over all possible values of a outside. So let's evaluate the sum on the inside, where we sum from b equals 0 to infinity. Then, it's two geometric sequences. The inner sum is 1 over 2 to the a plus 1 over 2 to the a plus 1, and so on. And we get that this geometric sequence sums to 1 over 2 to the a minus 1. And now we can throw this right back into the outside sum. With outside sum, we now just sum 1 over 2 to a from a equals minus 1 to infinity. And now we get 4. Yeah, that's what that factoring we have over there is one of the strategies we'll talk about later to deal with double sums. So yeah, as mentioned, one of the good ways to think about double sums is as the product of single sums. Another important way of thinking about double sums is to treat them as a single sum. What that means is that we can compute the double sum in different ways. It's going to take a while to compile, but. So if we list all of the numbers in the double sum out in this big 2x2 grid, then what the original double sum tells us to do is to sum across the entire first row, then sum across the entire second row. Yeah, so what the double sum says is to sum over fix A and sum B. So the first term inside of the double sum would, for A equals 0, would be 1/2 to the 0 plus 1/2 to the 1 plus 1/2 squared, which would be the first row of the sum. And then when A equals 1, the sum is 1/2 to the 1 plus 1/2 to the 2, which is the second row of the sum. So what this problem tells us to do is to sum the entire first row, then add that to the entire second row, and add that to the third row, and so on. Let's move on. So when evaluating double sums, there are a couple of things that we can do. So when we have a double sum, we have a lot of different choices of the order that we choose to sum the numbers. So for example, for the previous problem, instead of summing across all B, the summing across all A, we could have instead picked a different way to sum all of the numbers. We sum first 2 to the 0, then all copies of 1/2 to the 1, then all copies of 1/2 to the 2, and so on. So can we go back up to the matrix? So over here, it would correspond to summing along the top left diagonal, then summing upon the all terms on the diagonal containing 2 to the -1, then summing on the next diagonal, and then summing the next diagonals, and so on. So instead of summing across rows, we're summing across diagonals. And basically, when we have a double sum, it's very helpful to consider about all different ways that we can calculate the sum, rather than just the single order that the problem tells us to sum. Let's go back to the next slide. As mentioned earlier, another thing we can do with double sums is factor them. So if we have a double sum and the terms of the double sum are products, then sometimes we can factor the double sum into two single sums. For example, if we had to sum all the divisors of 1 million, then I think you'll need to recompile to load the sum. So the sum of the divisors formula is an example of factoring double sum. So if you want to calculate all of the sum of all the divisors of 1 million, then we have this double sum on the left-hand side, which encompasses all divisors of a million. All divisors of a million are 2 to the power of some number from 0 to 6 times 5 to the power of some number from 0 to 6. But now we can separate these two components. We multiply the sum of all the powers of 2 by the sum of all the powers of 5, and we get the sum of all the powers of 2 times the powers of 5. So with that said, let's move on to our first example, which is a problem from HMMT. So I'll give you a couple moments to think about this. If you have any ideas, type them into the chat. Yes, 2,310 is 2 times 3 times 5 times 7 times 11. We won't actually need this fact until the very end. The first part of the solution deals with the sum instead of 2,310 specifically. Yeah, so we can write this as 3 times the sum of A. So if we think about what this sum actually means, this sum is basically the sum of all the numbers that Kelvin writes down. So he writes down triples of numbers, and we want the sum of every single number that he ever writes down. So well, one useful thing to consider is how many times does a given number appear in the sum? That is, how many times does Kelvin write down a given integer n? So how many times does Kelvin write down the number 1, for example? Well, the number of times Kelvin writes down 1 is equal to 3 times the number of times that he writes down n 1 is the first number. So basically, Kelvin writes down a bunch of numbers on his sheet of paper. And we want the sum of every number that he ever writes down, which is what this sum encompasses. Dirichlet convolution is something fancy, then we won't really need it. So yeah, don't get too worked about it. So how many times does a given number n appear? It's 3 times the number of times it appears as the first number in the triple. N can be the first number of the triple, the second number of the triple, or the third number of the triple, all an equal number of times. Let's just count the number of times that n appears as the first number of the triple. So suppose that A equals n. How many choices do we have for B and C? Well, we know that ABC has to be equal to 2,310. So BC is 2,310 divided by n. How many choices does that leave for the pair B and C? The number of ways to choose B and C is equal to the number of divisors of 2,310 over n. We'll use this symbol tau of 2,310 over n to denote the number of divisors of 2,310 over n. This is because we can just choose B to be one divisor of 2,310 over n, and then that determines C. So the number of ways, number of times Kelvin writes down n as the first number of the triple is tau of 2,310 over n. That means the total of number of times he writes down n is equal to 3 times this number. You can write down n as the first number, the second number, or the third number. So now Kelvin writes down n a total of 3 times 2,310 over n times. So what we want now is the sum of all of the numbers that Kelvin writes down on the board. The number of times Kelvin writes down n on the board is 3 times tau of 2,310 over n. So the sum of all the n's he has on the board is 3n times tau of 2,310 over n. So we want to sum over all divisors. Tau is the number of divisors of n. Yeah, so now we want to sum over all divisors of 2,310. And the sum is n times tau of 2,310 over n. So as mentioned earlier, we can factor 2,310 as follows: 2 times 3 times 5 times 7 times 11. So now this is actually pretty nice because now that we can write the sum like so. It's a little bit of a leap, but I'll explain it. So we just need to consider the number of divisors of 2,310 over n. So if n is equal to 1, then tau of n is 32. That's the first term in our sum. If tau of 2,310 over, if n is a prime, then tau of 2,310 over n is, tau of 2,310 over n is equal to 16. That's the second term in our sum. 16 times 2 plus 3 plus 5 plus 7 plus 11. This sum actually equals that after we factor it. We're just writing it out right now. The next, if n is the product of 2 primes, then tau of 2310 over n is 8. And now we have 8 times the sum of every single divisor of 2310. That's the product of 2 primes. And now we continue on until tau of 2310 over n is 1. And n is the product of 5 primes, which is 2310. Now we can factor this sum. It becomes a lot more convenient, like so. So this equals 2 plus 2 times 3 plus 2 times 5 plus 2 times 7 plus 2 times 11 plus 2, which is 16,380. But we have a factor of 3 out front. So we need to multiply this by 3 for the final sum. So that's it. The basic idea here was to consider how many times Kelvin writes down a given number on his board and sum based on all of these n. Does anyone have any questions about this? Well, we can move on to the next question then.
Actually, we're gonna take a short 5-minute break before we move on.
Okay. So how can we handle these terms? Any ideas? So let's see. I'm not sure if that's immediately useful, but okay. Let's see. I don't really understand the idea, but let's see if what we're about to do is similar. So all of the denominators are of the form of 1 plus something. 1 plus 5 to the 2, 1 plus 5 to the 4, so on. And what can we do with a fraction whose denominator is of the form 1 plus 5 to the something? Yeah, with 1 plus something, we can turn it into an infinite geometric sequence. Down. Yep. So if we have a term 1 over 1 plus 5 to the 2 to the k, then we can expand it as this infinite geometric sequence. 1 over 5 to the 2 to the k minus 1 over 5 to the 2 times 2 to the k, and so on. So let's do this to every term in this sequence. So we've expanded all of the fractions in the sequence, and we get this infinite double sum. And is there anything special about the terms of this double sum? How well does this simplify? Yeah, if you look down the columns, the first term is 1 over 5 to the 1. The second term is negative 1 over 5 squared plus 2 over 5 squared, which is 1 over 5 squared. The next term is 1 over 5 cubed. And the next term, if you add it up, is 1 over 5 to the 4th, and so on. So actually, the entire sum just simplifies to this. And if you want a little more explanation of why this is true, the fact comes from that the numerators are all powers of 2. So if 2 to the k is the largest power of 2 dividing n, then a coefficient of 1/5 to the n is the negative sum of all the powers of 2 from 1 to 2 to the n minus 1, plus 2 to the n, which works out to 1. Yep. Let's see, my bad. The indices in the sum should be k. So the sum is by the infinite geometric series, just 1/4. Does anyone have any questions about this? If not, then let's move on to the next problem.
All right, so we're gonna be doing this next problem for now. So I'll give you a bit to look at it, think about it, and then we'll start going over it. Also, if you have any ideas, feel free to just share them. Yeah, so we can multiply 3 infinite geometric series, but like in particular, which ones are we looking at, right? Because we have to somehow get there, right? Because if we just take this directly, this is not that nice of a product, right? It's not as clear as to how we could factor it, right? But if we could maybe rewrite it in such a way that we can easily factor it, that'd be much nicer, right? Because the main condition that's bothering us is the fact that A less than B less than C, right? Like if we can get rid of this, then that would be nice, right? And that's why like those don't work, right? Because you need A less than B less than C, so you can't just directly multiply those 3 summations, right? So this problem's a bit trickier than that, but what we can do is well, we want to somehow get rid of that condition, right? So in order to try to get rid of that condition, we can maybe just consider the differences, right? So if we consider the differences, well, if we just look, right, ABC as A plus X, A plus X plus Y, well then now A, X, and Y are all at least 1, right? And then, so this is much closer to what we would be able to factor, right? Please try to stay on topic in the chat. Yeah, but so if we substitute those in for A, B, and C, or specifically B and C, well then we got this summation, right? And this summation, it looks a lot better because instead of having that ugly A less than B less than C stuff, we just have a bunch of stuff that goes from 1 to infinity, right? And we like this a lot more, right? So so what we will do is we will simplify it, right? And well, basically combine all the exponents group them by their variable, right? So we put all the a's together, all the x's together, and all the y's together, right? So yeah, and then this is a lot nicer, right? Because this is basically exactly what we are able to factor, right? Like we have these three independent sums and then we can just separate them, right? Because we need them to be independent before we can do any separation like that we would want to be doing, right? So if you scroll down some more, you'll see the factorization, right? But basically from here, the problem is just solved, right? Um, because now each of the individual geometric series is easy to calculate. So now put together, it's just easy, right? So does anyone have any questions on that? No? Okay, then I guess we'll move on. So this is our next question. So again, if you have ideas or something, feel free to just share them, and then we'll be discussing it. Yeah, exactly. Right. So, well, yeah. So if we remember what happened with the Kelvin the frog question, right, where you wrote down each of the A, B, and C's, and then you summed over the A plus B plus C. This is kind of the same idea, right? Because now it doesn't matter whether you're summing each of the AIs or you're just summing 7 A1s, right? Because if you think about it, it should be symmetric, right? So we just split it into 7 terms that all just look like that, right? And then this is, of course, 1/7 of the answer, right? So now where should we go from here? This should now be much better to work with, right? So ideas. Right? Yeah, so we see that we can split this even further, right? Because the denominator is just the product of a bunch of exponentials, right? And then the numerator is just A1, right? So we can factor this again, right? It's basically the same thing as before, right? So we can factor this into some big product of 7 terms, right? But this isn't actually, this is like much better than before, right? Because now instead of having like 7 iterative summations, we just have 7 separate summations. And we actually see that 6 of them are the same, right? So this is like much nicer than before. And this is like, we prefer this much more, right? So now this shouldn't be too hard to calculate, right? Because, well, 6 of them are all just the same geometric series, right? You don't see why we can't, yeah, because they're symmetric, right? If we think about it, the first bullet point, that summation, that should be the same no matter which AI you put in the numerator, right? So then you just, if you add them up, it should be symmetric. Does that make sense? The idea is basically all the AIs are the same. So then if you just consider one of them, that should be 1/7 of the total, right? And yeah, so I also saw someone mention that the six of the summations are equal, right? So they're all just equal to the same geometric series that evaluates to 3/2, right? So that's nice. And now, so we're just left with the first one, right? So, yeah, the answer is not that nice, but the algebra is fine, right? Yeah. So the first one, it's the same one as the one that we saw at the beginning of class, if you remember that, right? It was basically S, right? So we could go through the same process of like multiplying it by 1/3 and then taking the difference and then seeing that to geometric series. But you like we should know how to do that. It's like the same idea as before, basically, right? So if we calculate that, we plug that into the thing that we found above, and then we see that it's 3/4. Right, so now we're basically done, right? We have calculated each of the terms that we want, and now we put it all together, and then our answer is this ugly fraction, right? But yeah, so yeah, the question itself is not that bad until you get to like the last step in computations. Although it's only 7 times 3 to the 7th. So if you have like 3 to the 6th or 3 to the 7th memorized or something, then it's not actually that hard to calculate. Yeah, 3 to the 7th is like it's only 4 digits. It can't be that bad, right? But like 4 digits times 1 digit. But yeah, so well, 4 digits is only one more digit than Amy, right? So like you should be pretty used to it by now. But yeah, exactly. So 729 is 3 to the 6th, and then multiply that by 3 and then by 7 again or something. Right, so the computation is not actually that bad, but that's about it for this question. Right, so does anyone have questions on that? If no one has any questions on this question, then I guess we'll move on to the next question.
Okay, so now we're gonna cover a few more problems that didn't feel really fit into the sections that we had, but they're good problems to include. So first we have this question from APMO. So I'll give you a minute to read it. Okay, so does anyone notice anything interesting about the fraction in the sum here? Yeah, so it looks like a cube. So the denominator sort of looks like 1 minus x sub I cubed. And so we can try to make it that by, so we can write the denominator as 1 minus x sub I cubed plus x sub I cubed, so that we get 1 minus 3x sub I plus 3x sub I squared. And then we note that the form we were given is x sub I is I over 101. So that means that 1 minus x sub I is really 1 minus I over 101. as Brian said, which is also 101 minus I over 101. So that's x sub 101 minus I. So we can rewrite it as x sub 101 minus I cubed plus x sub I cubed. And so I've rewritten the sum there. So does anyone have any ideas for how to go from here? Yeah, so someone said to pair up the terms. So we noticed that if we add like the first term and the last term, or like the second term and the second to last term, if we add those two terms up, we just get 1, like this. So that means that we can pair up all of the terms so that they add up to 1. And so the whole sum has a total of 102 terms. So we're gonna have, so when we pair it up, we're gonna have 51 pairs. So the sum is 51. So does anyone have any questions? Okay, I guess not. So we'll move on to the last question we have from the 2007 Amy. So I'll give you a moment to read it. So yes, we'll have to bash eventually, but that we're gonna leave that to the end. Like right now, we should try to understand what this function, like what numbers this function sends numbers to. So first, so the first thing we can do is try to rewrite the inequality that they gave, so we can remove the absolute values. Yeah, so this is the closest integer to square root of p. So once we remove the absolute values, we have this. And so to determine like what values of p work such that b of p is k, we have to square both sides, as I think Alex said. So if we square both sides, then we get k squared minus k plus 1/4 is less than p, which is less than k squared plus k plus 1/4. And so since k is a positive integer, that just means that all of the numbers from k squared minus k plus 1 to k squared plus k work. So that's a total of 2k integers. So there's 2k integers such that b of p is k. And so now that we've determined this, we can try to work on computing the sum. So so first we notice that we try to find what like the maximum value is. So let's try to look at b of 2007. So b of 2007 is going to be 45. So that means that from 44 squared plus 44 plus 1, which is 1981, to 2007, we have that B of P is 45. And so yeah, as I wrote there, 44 squared plus 44 is the largest number with B of P equal to 44. So that means that there's a total of 27 numbers such that B of P is 45. And for every smaller value of K, the number of values such that B of P equals K is 2K, as is written in the second bullet. So now if we look at the sum, we can instead sum through the values of K. So for K equals 1 to 44, there's 2K integers such that B of P equals K. So we have K times 2K in that sum. And then from 1981 to 2007, we have those 27 numbers give B of P equals 45. So we add 27 times 45. And so now we can just compute the sum. So we can use the sum of squares formula. And so after we do that, we just evaluate this. So it comes out to 2 times 44 times 45 times 89 over 6 plus 27 times 45, and that's 59955. So the last 3 digits are 955. So does anyone have any questions?
Okay, so it looks like there are no questions. So this was our last example for Summations A. So I guess we're going to end slightly early, but before you guys leave, we were wondering if you guys would be interested in having Summations B as well. So we're just going to add on to what we were talking about this week, along with some new topics such as generating functions and combinatorial interpretations, as well as number theoretic summations. So just type in the chat if you guys are interested in this, and we'll have Summations B next week then. Okay, so it looks like most people are pretty interested. So yeah, we are going to have a Summations B next week then. So stay tuned for that. And some reminders, join the Discord if you haven't already, and the problem of the week will be posted tomorrow at 3 p.m. So thanks everybody for coming. And